This is a short recorded session that I wanted to run through to give you some information that will be helpful for you on homework assignment number 2. So bear with me here and I'll get this started. I want to use this example that you've seen before. This is the one where we looked at blood pressure plotted versus age, and we went through some of the calculations on this to show how to come up with the linear regression model for this. So I'm just going to pop these up here because you'll be reminded of them when I do some other code that I'm going to show you here with this model, and then some changes I'm going to make to it too. So this is all things that you've seen, and you saw where this model was tested, and you know that it's very good. It's nicely behaved data. But now you want to look at some of the assumptions that are made about linear regression. And you pretty much know this is a good data set, it's a good model, and so the assumptions are going to be true for this particular data set. But then we're going to make a change to it, and we'll take a look at what that does. So the main assumptions that you need to worry about are the error terms in the regression should be normally distributed with a mean of 0 and a standard deviation of sigma squared. The inputs to the model are not random. We assume that there's no measurement error and that they are linearly independent. Well, we only have one variable here, so that's not a concern in this particular example. So the question here is, what can we do about assumption number 1? And the answer is, well, we look at some plots that'll tell us about this. But first off, we need to look at that distribution of those plots. The ordinary residual is the y sub i's minus the y sub I hats, and those are the estimated values according to your linear regression or your linear model. The standardized residuals here are represented by z sub I, and that's equal to the e sub I divided by sigma times the square root of 1 minus the p double i's, which are supposed to be subscripts there. And those should have a mean of 0 and a standard deviation of 1. And I'm going to show you how to calculate those p sub i's here in one of the other slides coming up. So you'll get to see where this all comes from and how it's calculated. But first, I just want to take a look at what the pictures will show. And I'm going to go through some of these calculations with Excel. The slides there will calculate the standardized residuals and also those p sub i's. And it won't show when I'm just looking at it here, but you can double click on the Excel view that's here, and then you can copy paste that into Excel, and you'll be able to look at the embedded calculations. Now the reason I'm doing this is because this is summarized or given, I guess, in more detail in your textbook, but it's really hard to follow it. And it's hard to just keep in mind, well, what am I calculating here? Where does this come from, and how does it really fit? Well, if you got it in a spreadsheet, it's pretty easy to follow. And then you can see, oh yeah, this is where that comes from and how it lines up. And so that's why I'm putting it in this form for you here. So back to that model for blood pressure. Here's my data. Again, here's my predicted values. And those are the e sub i's, that's the y sub i's minus the y sub I hats. I calculate that mean square error here, and then those p sub i's, and you can look in the book to see what this calculation is, but you can also then look at it in terms of when you put this into Excel, so you can track it through there. So then we get clear over here, and we get to that standardized residual. And here's the calculation down here in a little more detail for those p sub i's. So it all looks kind of confusing, but the important thing is to take some of this and put it into a plot so you can see what it's telling you. So I'm going to plot the ordered normal 0, 1 versus the ordered standardized residuals. And it's a small data set, so I didn't do that plot there. But what I did do was I plotted the standardized residual versus the x sub i's, and that'll be on the next slide. And then 2 slides over, I'll have that standardized residual versus the y sub I hats, the predicted values. And then the plot after that one will be those standardized residuals versus the observation number, and that'll be over a couple more slides. And so what we're looking for in these is to see, is this well behaved, or is there anything that's going to stick out there and look out of the ordinary? And it shouldn't, because this is a nice data set and everything's well behaved. But the point of this is so that you can be able to take a look at this on your own. So here's those standardized residuals, the z sub i's plotted versus the x sub i's. And you can see there's nothing really jumping out here as being very big. So it's a nice plot, and it shows you, yeah, you got a well-behaved data set here. Standardized residuals versus the y sub I hats, same deal. Nothing stands out as jumping way out there as being like several standard deviations out. It's all within a good tight range, minus 1.5 to plus 1.5. Nice picture for the data set. Just a quick way to look at that to see if some of these things might jump out that would indicate that there's a problem in that data set. Standardized residuals here versus the observation numbers, and again, everything's within a pretty tight range. So now what I want to do is, I want to talk about a little bit more here for the high leverage. The highest value there for the p sub I is 0.6, but if you look up in your book, you need to compare that to 2 times p plus 1 divided by n, and that's 0.8. And this is on page 109, 110 in your textbook there. So as long as my p sub I values are less than this number, there's no indication of high leverage there. So it's just a little calculation that you can perform here that is, not too great, but it doesn't indicate anything with this data set. All right, high influence. You want to calculate the effect that it produces on the fit when each data point is deleted. And that's really a lot of work, and so I don't want you to have to do that. So we're going to figure out how to do this with Python. And you're going to look at either Cook's distance or what's called diffets, and these are both discussed in your textbook. A lot of calculations to do here to come up with this, but let's let the software do it for us and see what we can find here. Okay, I'm going to look at 2 different data sets. The BP data was the one that I just ran through that's very well behaved, but then I created another data set from that where I stuck in an outlier, and we'll see what happens when we have that outlier in there and how we can detect it. Here's my data, my Python code to work with the original data that's nice and clean, and so I just put that code in there so you can run that. And here's the result of that linear model, and it's got that same intercept and age coefficient, so this is what you've all seen before, and it's got a nice R-squared value. Very nice model. And here's what it looks like if I show a plot of it, where I have the actual data in blue, and then the fit to that, the linear regression, in kind of an orangey color there. And it gives a really nice picture, which as we expected it would. And then I also ran Cook's and diffets for this very nice database. And where you want to look in here, you want to look at Cook's D, and you see there's nothing really standing out there in terms of being a big number. And then the same thing over here with diffets. These are all pretty small numbers, indicates nothing really going on. So now let's go to another picture here for leverage, and I've given you the code up here to do this in Python. And you're looking at a plot here of points that are kind of as far out as you can get, and nothing shows up very far here. This is like 1.5, and it's a small size circle, minus 1.5 down here. Nothing very big in terms of influence that these plots would have here. So it's kind of a nice picture still, and that's for the nice data set. But now look what happens when I put in an outlier here. At age 45, I'm sticking in a blood pressure reading there of 185. And so I take that data set, I run my linear model. My model is quite a bit different than what I had before. my R squared is really bad because I got a really bad data value in there. And so I made a plot of it too. That 45, 185 is that point right up there. And what I want to know is, can I detect that by looking at some of these other plots that I've just been showing you? So we're going to run those and run it against this data set and see what we come up with from there. Got a bad data point in there. And so here's Cooks and Diffets. Now, with Diffets, this second data point really shows up as a big number over here. It's not quite as well reflected with Cooks D, but remember, this is kind of a small data set, and you're using this to kind of scan to see if there's something in there that should be dealt with, and so it's indicating that, well, maybe I've got a problem with or the second data point, or maybe it's because they're not lining up very good with the rest of the data, and so it's not very definitive in terms of Cooks D, but it is definitive over here in terms of Diffets. So you get a pretty nice picture of that. All right, one more picture here. Here's that leverage plot now, and it doesn't show up as being anything really huge until you start looking at the scale over here on the left. So this is showing standardized residuals way up there at 17.5, and that's a pretty big blob up there, indicating you got a point that's very, very high leverage out there. So it's telling you there's quite a story going on here, and there's a lot of difficult reading in your book about these topics, and so I'm going to post this for you, and then I'm also going to give you a copy of these slides so you can come back and take a look at it. See if I'm to the end here. Looks like it is. All right. Enjoy that, and I hope it's helpful to you in your reading. And I'm going to also post an announcement here that's got some other details about your work on homework number 1, what I saw there, and then what I'm expecting here in homework number 2. So hope you enjoy it. You've got several weeks now to work on the same data set and come up with some even better models than you did before.